Hello everyone, how are you? Just double checking, do we have sound connection here? Yes, we do? Okay, excellent.
The microphone's a little off.
It's low?
It's like lower quality.
Really? So you're saying the microphone is lower quality today?
No, you sound like a robot.
Oh no.
There's maybe some office hours too.
Oh, you guys should have told me in office hours. Let me fix this. So you're... I know what's wrong. Just a second. Is this any better? Does this make it better?
That's better.
It's better? Okay. It's because of some kind of amplification. Is it too quiet now though? Little quiet. Let's crank it up. Okay. I think I see this. It's because somehow the audio settings get adjusted. So I'm gonna tweak it this way. Is it still like a robot or is it okay?
Just a little bit.
A little bit. Pulling it back. How is it now? Is this like good now, or is it like still a little bit wonky?
Still kind of sounds a little bit wonky, but
Still a bit wonky. We'll go anyway with this thing. Unfortunately, it's that somehow the audio settings got adjusted by the computer. I'll try this. Okay, let's leave it this way. Good. Let's go here. Yeah, and actually, in general, if you guys are at my office hours and notice that anything is funny, please let me know, because we can use that to help for the class too. Okay, great. Well, hello everyone, and we're going to talk some more about combinatorics today. Just so that you know, we've finished the pigeonhole principle part, and just a few comments. Some people did come in the office hours, and when they came in the office hours, I made some comments that there are some problems that are there that are meant to, I guess, practice induction or pigeonhole principle or something. So that's just something to think about, could be useful as hints. And then today we're going to move away from those two topics. We're going into another topic. Now the thing I'm going to talk about today is actually something for which, good, that works. It's something for which I've actually talked about this in the Putnam class already. I talked about it in the, oops. Yep, that's right. I talked about it in the Putnam class already for this group. So if anyone has seen that before, I'm sorry, you're going to get it again. But well, hopefully it'll make more sense the second time. But I want to talk about it because it's a really, really interesting application of a very interesting idea from combinatorics. So if you've seen this before, please don't give away anything because it's just awesome. So the setup for this is we want to, as you can probably tell, my goal is to teach you combinatorial ideas, but I always want to show you the combinatorial ideas in the context of some like very surprising application. It's like how when I was trying to show you guys induction, I guess we ended up talking about things that involved matrices and like these like numbers with no two digits same next to each other but are even. And then when I wanted to talk about the notion of pigeonhole principle, we went and talked about this Dirichlet's theorem about approximating real numbers. And so today I want to teach you about another idea in combinatorics. You won't know what the idea is yet, but we'll start with an application. And the application is called getting into college. So it used to be that there was no SAT, there weren't all these exams, and so every university had its own kinds of exams to go and try to figure out how you get into the university. So Carnegie Mellon was no exception. And on the Carnegie Mellon exam to enter the university back in like the 1913-ish time, I think, there were all kinds of questions you had to answer. Some of them were things like solving an equation. Sometimes it was like draw a graph of something. But amidst that exam, like in the middle of the questions, not at the end, there was the interesting question which said, you have a spherical triangle with angles of something like 70 degrees, 80 degrees, and 110 degrees. Okay, you have this spherical triangle, and the sphere has radius 10. What is the area of the spherical triangle? By the way, this was one of the questions to go and see who would go and get into CMU. And I remember when I saw this exam, I said, oh my gosh, I will have some trouble getting into CMU. What's this about? Well, first of all, what's a spherical triangle? I guess we've got to think about a sphere. And again, those of you who saw this particular thing in the Putnam class, it'll be the same idea. However, it's just so important that I want to talk about it in this class. So what's a spherical triangle? Well, a spherical triangle is you get a sphere, and it's supposed to be a sphere, so I guess it's round. And a triangle on the surface of the sphere means that you have 3 points. Okay? And now it's a triangle, meaning that you have the shortest paths between the points. As you know, if you fly around on airplanes, these straight lines are not really straight. They're actually over the surface of the Earth. And anyone who has ever noticed, if you fly like very long distances on the Earth, it looks like the plane is doing this, right? It's kind of going up and down because that's just the shortest path. Actually, I used to fly to China a lot, and I just noticed that the shortest path between New York and Beijing was to go over the North Pole. And that was just like how it always was every single time. But so we have this spherical triangle, and then these angles are something like 70, 80, and 110. And the question was, what's the area? If you've seen this before, don't give it away. If you haven't seen this before, jump in. Just feel free to type raise hand. And by the way, the answer, you don't have to have an answer. In fact, almost nobody should know what the answer is. Almost nobody. Andrew. Okay, that is the direction we're going to go in. So let's just say equivalently, calculate the fraction of the surface area. Right? Because there is a formula for the surface area of a sphere. The total surface area of a sphere has a formula. Does anyone know what it is? 4 pi r squared, that's right. So the surface area of the whole thing is 4 pi times r squared, which, by the way, the proof of the surface area thing is also interesting on its own. We just won't go into that here today. But if I can just find the fraction, I'm in good shape. All right. So then, if you haven't seen this before, how might you hope to find the fraction? Christopher, were you going to answer the surface of the sphere, or did you have another idea?
No, I was going to say the surface area of the sphere.
No problem, no problem. So it's 4 pi r squared. And now, by the way, I don't expect any answers. This is something which I didn't know how to do either the first time I saw it. But I'm just kind of curious. Does anyone have things what kinds of math could be useful to solve this? Feel free to just type raise hand or RH, and I'll call on you. And don't be afraid if you don't know how to do it, because that was the whole point. Ben. Uh-oh, I can't seem to hear you, Ben.
Oh, sorry. Yeah. So a triangle is made up of 3 lines.
Yes.
Or I guess on a sphere, we look at a great circle.
Mm-hmm.
So maybe you could, because with one line you divide the sphere in half, right? The area in half. So maybe you could figure out some sort of formula that divides the sphere, given multiple lines.
Aha. Okay. So one line cuts. Let me put line in this quotes, cut sphere in half. Okay. By the way, I'll get more ideas on this right after I explain what Ben just said. Ben said something about what is the shortest path on a sphere. Like when you draw these lines on the sphere, what are they really doing? They're called great circles. So actually, if I want to know the distance between 2 points on the sphere, what you do is you find the circle that goes through those 2 points, which is like an equator. It goes all the way around the sphere. The center of that great circle is the center of the sphere, and that would be the shortest path between those 2 points. So here's an important fact that we are going to use. Fact. Oops. fact. The shortest path between 2 points on a sphere is the great circle through them. And a great circle is a circle which is centered at the same center as the sphere, with the same center as the sphere itself. Okay? And I'll dwell a little bit more on this fact after I hear another idea. Venkatesh, did you want to say something?
I think I had a similar idea, but I was also thinking, like, for 2D, like if it was just a circle, you could consider it kind of like a sector, right? Like the length of a sector. So maybe you could like apply similar techniques to get like the lengths of all the stuff, and then maybe find the area.
Okay. Let me put another idea for the 2D version. The 2D version, what I'm hearing from you is you're saying like, look, if I drew a circle and I have like some part of a sector, like I'm not doing surface area anymore, I'm doing perimeter-ish, right? I think your idea was, what's the 2D version of this? The 2D version of this is something like, I've got a circle, I've got a portion of it, and what kind of formula do you use to find the portion of it? The length of that part of the circumference, well, that turns out to be a fraction. That's just a fraction of the whole circumference, and the fraction has something to do with what angle that is out of 360 degrees. Does that make sense? That's an interesting idea. This thing here, the fraction is, let's write an angle. Every good angle is theta. So theta over 360 degrees. Okay, so that's an idea. It's like the fraction of the circle's circumference that you're talking about is just like the fraction of the angle divided by the whole 360. Let me now go into this point that I said about how this great circle, because not everyone is used to thinking about 3D geometry. That seems a little bit counterintuitive. Why would it be that the shortest path uses the great circle? Well, here, this is not the main point of this class, so let me just briefly explain to you why you should believe this fact. This class is not a geometry class. We're just going to use the fact. But just in case you're curious why that should be, the easiest way to think of it is, look, suppose I'm trying to go between 2 points on the Earth. If the 2 points on the Earth are just kind of like New York and Istanbul, somehow they're just like random points, right? And it's hard to know, why should it be that the shortest path between New York and Istanbul is just this great circle? It's a lot easier to think about the fact that the sphere can rotate. So what if you just took the Earth with New York and Istanbul, and we hit it with a huge asteroid until New York was at the North Pole? All right, now actually you need a really huge asteroid if you think about the physics of this. But anyway, so let's pretend we moved New York all the way to the North Pole. Istanbul is now all the way over here. Is it obvious to people that if I rotated the sphere, and I have one point of the sphere which is actually legitimately at the North Pole, and some other point of the sphere, which is like somewhere else, is it obvious that the shortest path between them is to just go north? Does that sort of make sense? It's like, suppose I have a sphere, I have this New York and Istanbul, it's too confusing, so rotate the whole sphere until New York's at the North Pole. Now you got Istanbul over here. How do you get from Istanbul to the North Pole? You go north. Does that make sense? But now if you imagine what happens as you go north, the shortest path obviously just goes north, and it's going to, this is like in the back. Does this make sense what I've drawn here? I just said like the path that goes from wherever that other point is up into the North Pole, the shortest path really is just go north. And then like by symmetry, there's this entire circle which is going around. That's like a line of longitude and the opposite line of longitude. Did that make sense? I hope this helps to explain why it would make sense that the shortest path between 2 points is actually the section of this great circle which connects them. And a great circle just happens to be a circle which has the same center as the center of the sphere. Another way to think of a great circle is as if you sliced the sphere with a knife and the knife actually went through the center of the sphere, what you chop off has these two halves. Okay? And this is just trying to show you why that would be the case. Fun fact, the great circle also is the circle that goes through these 2 points, which has the longest circumference on the surface of the sphere. You know, there are other circles that go through these 2 points. Like there's one that just goes around on the surface of the sphere like this, and that happens to be a smaller circle. So the great circle is actually the longest one. However, from the point of view of the path between them, it's the shortest path between them. All right. I said all of this because I want everyone to be able to use these facts. Somehow, if I just had one of these lines, I cut the sphere in half. And the idea was, what if I have a bunch of these lines? How does that cut the sphere? Okay. Well, we still need to keep figuring out how to solve this problem. So what else can we do? Well, here's a suggestion. Whenever you get a problem that's hard, you try to ask an easier problem. And if you've seen this before, I'm not going to call on you just because I would like to let everyone else play, if that's okay. It's just much more fun that way. But whenever you have a hard problem, start by trying to solve an easier version of it. And that's also a general hint of my homework problems. They are hard, but if you kind of think of smaller, simpler cases, you can make progress, and then you carry that along. What might be an easier version of this kind of a question? This question here says I have a 70 degrees, 80 degrees, 110 degrees, and it's a circle. I mean, this is on a sphere, got some radius. What's an easier version of a problem that I could try to solve? Ben?
What about just using 2 lines? Instead of like a triangle, we just use 2 lines.
Okay, let's go and do an easier version. Easier version. Well, let's go and take the sphere. And you want to do 2 lines. How do I make 2 lines? Now you use the fact that each line is a great circle. Each line is what you get when you slice this thing with a knife that goes right through the center. So I'm going to draw 2 of them, okay? I'll say that one of them maybe looks like this. Okay, now it looks more like a sphere. And I'll draw another one. Another one which maybe cuts across this way. Okay, so what I've just drawn here is that this is a sphere, and there are 2 of these lines that have gone through it. And I've cut the sphere actually into 4 pieces. As you said before, if I just looked at just the green cut, I have half and half. If I looked at just the yellow cut, I have half and half. Oh no, this is a really dumb picture because now it looks like they're all quarters. I don't want all quarters, okay? I'm going to draw you another one that's not obviously all quarters because then that's too obvious. Oh man, at first I was going to be like, erasing is going to be a pain because of all those dotted lines, but then I remembered I have the undo. Undo is very powerful. Okay, undo, and now I want to make something that's not obviously 90 degrees. How do you do that? Guess like this. Okay, so now I have this. This is very obviously not 90 degrees. And suppose what I'm curious about is like, what's the surface area fraction that happens to live over here? And also in the back. Does it make sense what I've drawn? I've been like, there's some surface area over here, and there's also some surface area in the back. What fraction of the sphere is that? Is there an easy way to quantify that? You can express it in terms of something. Dhruv.
So we know that just like let's use like the green circle for example. The bucket is 50% lower to 50%. So that angle between the green and the yellow, however much that is, I guess over 180 would be that percent and half the circle.
Okay, let's give that angle a name. We'll call it theta. Okay, so what you're saying is that the fraction that I've got is theta divided by 180 degrees divided by half. Is that what you're, sorry, times a half, or like divided by 2. Is that what you're saying?
Yeah.
Fraction of area is equal to, you said it's theta over 180, and then times a half, because it's of a half of the whole thing, which I can rewrite as theta over 360. Everything's in degrees, so everything's just degrees here, even though I don't write the dot. Oh, Francesco, were you going to say something?
Yeah, the same thing.
The same thing. Did you have a different way of explaining it?
I just looked at it as like, since like there's the corner, there's the two lines intersecting, and they're essentially like you can flatten it into a circle and just look at the angle there.
So you're saying it's theta over 360 because it's 360 for the whole thing. Is that what you mean?
Yeah.
Yeah. And actually, if you think about it, you do see this. If you ever eat oranges, when you slice the oranges into wedges, which is how my family used to eat oranges. But then I don't eat oranges that way because it's really messy and juice goes everywhere. But somehow, if you slice it into these fractions, the amount of peel you get is totally obvious. That it's like the amount of peel is the fraction called the angle divided by 360 degrees. That makes sense. Actually, this is a really good idea. So now we know how to do it with just one line, one circle, or a great circle, is half. How to do it with two great circles, it's just going to be the angle divided by 360. So now what could we do with 3? Well, actually, it's not super obvious, because if I make the third one cut into this in a really weird way, it's bad. But are there other ways to make the problem easier? Right? We have to do this problem that was over here. It has 3 of these great circles all cutting each other, 70, 80, 110. Is there any other type of easiness I could take to this question? Like, to make it easier, ask a different question and get some intuition. Andrew.
You like make the triangle like an equilateral triangle?
What do you mean by an equilateral triangle? What angles?
Like 60, 60, 60.
Okay, actually, let's start with that. Okay, there's another way to do this, another way to approach the whole thing. We can also try other numbers. Okay, what if I have a 60 degree, 60 degree, 60 degree on the sphere? The first question is, how do you do that? I like your thing you said, because it's going to get to a point. Out of it.
You can't.
You can't, because the Earth isn't flat. So this is actually really interesting, okay? But I wanted you to say that point because I was actually going to use that triangle. You sort of can, because the Earth looks flat. I mean, like if you just went to the floor near you and you just did, okay, 60, 60, 60, you're good. But the interesting thing is that it's not flat. Oh, there was another person who was going to say some stuff. And let me get your name right. Andres? Is it Andre or? Andres, what were you going to say?
Could we do a 90, 90, 90?
We're going to go there too. Okay, so I want both of these. So the first one is this, hold the 90, 90, 90, okay? I'm going to get to that next. Let me draw this guy. What does this look like on the sphere? In fact, the only way to get this on the sphere is to make the triangle look like this. See, it's over there. It's really, really, really small. In fact, it's practically inconsequential. Does that make sense? The only way to actually make a triangle that is flat on a sphere is to get so close together that it looks flat. And you're still not at 60, 60, 60. It's like 60 plus a tiny bit. So in this tiny thing here, what this actually is, zoomed in, is something like this, where each of them is 60 plus a bit. Okay? But it's 60 plus a bit, 60 plus a bit, 60 plus a bit. And what I'm going to say about this is that the fraction of the area is about 0 plus a bit. Okay? And actually, by the way, this is how people try to figure out like whether space is curved or flat. I mean, in general, if you are measuring the angles of a triangle, if the sum of the angles of the triangle is bigger than 180, then that's actually positive curvature of your space that you're in. That's actually what this is. So when people are curious, like, is the space we live in flat? In some funny notion of flatness, people are launching satellites to go very far apart from each other and measure the angles between them. And there's even like examples of this. If you look at some of those pictures that they draw of the universe, where there's like light going around a star. I'm not sure if you guys know what I'm talking about. Like sometimes there's a picture of a star and a gravitational well, and like light rays can curve as they go by the star. These are all notions of, is space flat or curved? And so the notion of the sum of the degrees of the angle of a triangle is actually very fundamental there. But so we found 60, 60, 60, about 0. Now let me go to Andres's idea. Andres's idea is there's another kind of a triangle we could have, or a 90 degrees, 90 degrees, 90 degrees triangle. Well, that one looks quite interesting. For that one, we go and take the North Pole. And then we also take the front pole and the east pole. None of those actually really exist. But you know what I mean. Like the North Pole, the front pole, and the east pole. A sphere can only really have north and south poles because that makes an axis that it revolves around, but I think you guys get the idea. Oh, in space, can you have the sum of the angles be less than 180? Yes, you can out of it. That's called hyperbolic space. Yes, that's called negative curvature. So the interesting thing is that this whole notion of sum of angles of a triangle is deeply relevant to geometry, like geometry of... Actually, there's a name for it. It's called non-Euclidean geometry. But anyway, that's not the topic of this course. So now the 90, 90, 90, what does that look like? That's like you just go down from the north to the front to the east, and the east to the north. And somehow, all of these are 90. This is what I call the rightest triangle in the world. It's very right. It's 90, 90, and 90. You can't get any better than that. But now, what fraction of the surface area is this? This is easy. Like this one, if it's 90, 90, 90, you can say what is the fraction of the whole surface area, just like by looking at it. Yes, thank you. Zhejia, it's 1/8. Okay, so the 90, 90, 90, this is fraction 1/8 of the whole. It's 1/8 because you can sort of see that across the top hemisphere, northern hemisphere, you put 4 of these guys. And then you put 4 more on the bottom, so it's 1/8. Okay, so now can we find any interesting patterns? 90, 90, 90 gives me 1/8. We saw 60, 60, 60 gives you like 0. But we need more data. What I'm trying to say, by the way, is that this question was on an exam, therefore it has actually got a simple formula. And the question is how to guess the formula. In order to guess the formula, we need more data points. Can we think of any other triangles that we can make where we can like get more examples of angle, 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 fraction, and we can find a pattern, and then we'll prove it. Again, I'm going to try to call on people who I know haven't seen this before. Aha. Sean.
You can have a 120, 120, 120 triangle that covers the whole sphere.
Oh, you said 120, 120, 120 covers the whole sphere.
Yeah.
How is that?
You just have all three angles at the same point, and they go outward.
Oh, yes, 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 yes. Okay. I know what you mean. Here's the sphere. Here are the 3 points. They're like all at the same place, okay? 3 points. But actually, if I zoom in and I ask what's actually going on here, what you're telling me is that these 3 points, there's like some triangle-ish thing here, but this is the inside. Does that make sense? Is that what you're saying? That's sort of like if you just decided to put on your socks inside out. It's not that your socks are inside out, it's just that everyone else is wearing your socks. Okay? So now, but if you do this, okay, there's one thing I want to adjust. That's cursed. Okay, yes. So something else I want to do with this is, you said 120? I want to adjust your numbers a little bit. Not quite 120. What do you actually mean? Like that's not 120. 300. Yes, that's 300. Okay, but it's the correct principle, all right? So 300, 300, 300, that corresponds to fraction, I'll call it 1 minus. Actually, all of these are 300 minus, 300 minus, 300 minus. They're all like marginally less than 300 because of the fact that this is still like outwardly bulging. It's not flat, right? The Earth is not flat, it's outwardly bulging, and so each of these is like eaten in a little bit. So it's a little bit less than 300. All right, so 300, 300, 300, I get a fraction of like about 1. 60, 60, 60, I get a fraction of about 0. And 90, 90, 90, I get 1/8. Can we do anything that's like not equilateral? Ideally something that involves like a variable thing. I have a hint. The hint I have is that this thing over here is really useful. Can we do something with that? Now I want something where it's not just like all three of them are fixed constants. In fact, I'd like one of them to be a theta. Okay, Andrew.
Could you like construct it so that like you're moving away in like an arc that kind of like where like the center of the arc between the two lines would like intersect with the center of the angle? I'm explaining this terribly, but I'm thinking of like maybe it's like if you were to split the triangle in half down the center of your original theta, you would get two equal angles.
Okay, are you saying like use this picture or like another one? Do you want to use this picture? This picture. Are you saying split it where you kind of slice the orange peel in half this way? Is that your half you're talking about?
Like the maybe like split the purple thing in half.
Ah, so you mean like you want to cut it so you have like two 90-degree angles. Is that what you want to do?
Yeah.
Let's do that. The easiest way to think of that is like, let's put this guy into the North Pole. Okay, that's exactly what I wanted, by the way. So, and by the way, there's no like right or wrong answer. There's no, we're just experimenting. But here's another thing you can do. You can take the Earth. You can run two of these things coming down. One there, another one there. Okay, and there's a theta here. And at some point they hit the equator, right? And these are right angles. Did that make sense to people? Like that's a totally legitimate way to make a triangle. I have two of these lines of longitude and I have the equator. Okay, so that's a theta 90, 90. What fraction is that? What fraction does theta 90, 90 correspond to? Jack.
Looks like half of what we had for just the theta triangle.
Half of what we had for the theta triangle, that was theta over 360 before.
Yes, I guess 720.
Theta over 720. Okay, so now we have a lot of information, and now we can pretend that we are not mathematicians, but like people who look at numbers and try to find patterns, okay? So we found out that from theta 90, 90, you get theta over 720. What other data do we have? We also know that 60, 60, 60 gives you about 0. Okay, we know that this 300, 300, 300, that gives you like 1. We know that 90, 90, 90, oh, 90, 90, 90 is there. That's theta over 720. Because, oh my gosh, it actually works. 90, 90, 90, like over here, it's like 1/8, right? 90 over 720. So this one actually also matches 90, 90, 90. Okay, so then the key question is, what kind of formula could the answer be? And I'll give you a hint. The formula turns out to be really easy. It's an even easier formula than the quadratic formula. There's no square roots in it. You just have to like add some stuff up and like divide or subtract or something. Sean.
It looks like it's linear.
Ah, it looks like it's linear.
Calculation.
It's linear. Yeah, you're doing some linear interpolation. There's some linear stuff in actually the sum of the three angles. Okay, so actually, let me drive towards the answer. You know, we've been talking about comparing the sum of the angles to 180 degrees. And there's something very practical about being on the surface of a sphere. Remember I said there's no way to make the sum of the angles equal to 180. You're always more. And the only question is how much more. In the 300, 300, 300, you're like really more. If that makes sense. That was your example. It's like so crazy more. In the tiny, tiny thing, you're like not much more. In fact, it should sort of make sense that the how far off you are from 180 has something to do with how not flat you are. Does that make sense? That's a hint. Can anyone see a way to guess a formula? So there's actually a formula. Wait, where'd it go? The fraction is equal to something in terms of the angles, if they are A, B, and C, or alpha, beta, and gamma. Let's call that. Let's suppose that the angles are alpha, beta, and gamma. Can anyone guess something that might work, given that I gave some hint that it has to do with like how your angle sum differs from 180? What's going on here? Dhruva.
Maybe it's just so however close we are to 900 instead of 180, the sum of the angles, it will slowly approach 1 from 0 linearly.
Okay, somehow like linearly interpolating. Linearly interpolation? No. Linearly interpolating from like 0 to 1 as you go from like 180 to 900.
So I guess it could be like the sum of the angles minus 180 over 720.
Yes. So your formula is sum of the angles minus 180 over 720. Bam! That's the correct answer, okay? So by the way, this is like, what? So simple. So yeah. I mean, like this is when you look at it, you're like, wow, that's a really simple formula. How come we don't learn that in school anymore? It's actually really simple. It's just the sum of the three angles minus 180 divided by 720. And in fact, if we learned it in school, if you did that exam on the Carnegie Mellon, Carnegie Institute of Technology entrance exam, it would be like, it's easy. Got it. Actually, we don't learn this anymore because this entire area called spherical trigonometry has disappeared from our curriculum. It's just not taught anymore. The reason is because a long time ago, it was actually important. Long time ago, people sailed ships, 1913. That's like when they sailed ships across the ocean. They didn't have GPS. And so you had to know what angles were and like stuff like that. Or else if you sail the ship the wrong angle, you die. It's very simple. So anyway, that was like part of the curriculum. But not anymore, so it was just a lost art. But it's a beautiful formula. So now let's prove it. That's what we'll do with the rest of this. How do you prove this formula? Well, obviously you just use calculus, right? Well, unfortunately, calculus is like really painful. I don't see how calculus would ever give you a formula that talks about the angles. Okay? Calculus will give you a big mess of sines, cosines, and square roots, and like whatever else. It'll be horrible. So it turns out that the solution is to use combinatorics. And to use something that is like the next bunch of things that we're going to talk about. And you'll see where it comes from. So what I'm going to do is I'm going to draw a general triangle. Okay? So here's what a general spherical, that was supposed to say general spherical triangle. Here's what a general spherical triangle looks like. I just have to draw like a sphere. And I have to draw these like three things. Without loss of generality, I've rotated the sphere so that one of them happens to be the equator. I said the word without loss of generality because even if I have three like other things, I can just turn the ball until one of those things happens to be the equator cut. And then I've got two other ones, okay? So it's got something which is maybe doing this. And we have another one, which is maybe kind of sweeping around this way. That was supposed to look spherical, but close enough. Okay, so I've got these things. And now if I've got all of these things, I can say, well, here's a spherical triangle. The spherical triangle happens to be this guy. Does that make sense? So that's my spherical triangle. I'm saying any spherical triangle looks like this. You just take three of these cuts, slicing past the center of the sphere. All right. The first thing I want to do is I want to say when you do anything with math, you look for patterns. I claim that if you look at this carefully drawn picture, there's an interesting thing that you might observe. here's the spherical triangle I'm looking at. Do you notice anything like nice or elegant or neat coincidence about this picture? That's the one I care about. Sydney. Symmetry. There's the same thing in the back. You see that? That's true. Because of the symmetry, since I just sliced through the center of the Earth 3 times, if there's a triangle here, there's another copy of it in the back. Let's just like make a nice observation. There's another copy in the back. So now what I want to do is I want to define 3 sets. And the 3 sets I want to play with are going to be 3 sets for which their intersection is this piece in question. Actually, we're now moving into an area of combinatorics when you have 3 sets. What might you do if you're talking about combinatorics and you have 3 sets and you're dealing with intersection of all 3? Does anyone know like some fact from combinatorics about 3 sets and intersection of all 3? Aha, out of it.
Pi.
Wait, what did you say? Inclusion-exclusion. Inclusion-exclusion, right? So this is something I think most people have seen before in some other class, but I just wanted to show how this thing can come to life. And this is also a way to review it or to quickly see it for the first time. Here's an interesting fact. If I have anyhow 3 sets, let me just jump to another screen, okay? If I draw a Venn diagram and I've got 3 sets, A, B, and C, A, B, and C, there's some formula about A union B union C. Is that right? Like there's some formula. If I want to know like what is covered by any of the 3 of them, well, the answer is you take how much is in A plus how much is in B plus how much is in C, yeah? But then that's too much. You've overcounted because if I went and, this is a counting thing. The vertical bars is how big is my set, right? I've overcounted. So I need to subtract off the A intersect B, subtract off the B intersect C, and subtract off the C intersect A. Okay, but we're not done. From this, if you took all of the big pieces, and then you subtract off the parts that are in 2 of them, what else do you have to do? Is this something everyone has seen before, like in high school or concepts? Yeah, it should be somewhere. You need to add back something, okay? And we'll prove all of this next time rigorously. I mean, the purpose of today's lecture is to kind of open the door to inclusion-exclusion. This is called the inclusion-exclusion. Some people call it the principle of inclusion-exclusion, which is PIE, but you can just, it's just like add, subtract, we'll prove the whole thing later. Suvik, yes, thank you, you add back. Now, this is what you think of when you think about the sizes of sets. But actually, the same reason why this is true also holds if we're talking about areas. If I had 3 weird-shaped objects overlapping with each other, the area of their total overlap is equal to add up each area, subtract off the areas that 2 of them intersect on, and add back the area of all 3 intersected. Does that make sense to people? It's the same reason why counting would work. If you don't believe the area thing, imagine that you just had areas and regions and you had grains of sand spray painted on the surface. And you're just counting how many grains of sand do I have. Counting grains of sand is proportional to the area. So that's why it's the same concept. Now let's use it. So now I need to get 3 sets such that somehow their union and intersection is nice. And the 3 sets I want to use will look like this. So I'm going to have the first set A, which is the stuff which is underneath. Underneath like that green thing. That's why I'm using green for the A. For B, let's use the pink thing. For B, I want the stuff that is over this one. Okay, and for the C, which is yellow, I'm going to pick the ones that go over the yellow. Why did I do that? How can you describe the part I'm curious about? Is there a reason why I chose under for the green, over for the pink, and over for the yellow? Raise hand, Venkatesh.
The intersection is the gray shade.
A intersect B intersect C is our spherical triangle that said spherical. Triangle. Okay, so now let's go and use this inclusion-exclusion principle and just have some fun. So what we now know is if we think about the fractions, now we're not going to say those are areas, we'll talk about the fractions. So what I'm going to do now is I'm going to say for the rest of this, it's like the vertical bar x vertical bar is now going to mean the fraction of the area. Is that okay? Vertical bar is fraction of area. It's not the actual area. It's also not the size of the set. I'm just going to use that here. And the inclusion-exclusion principle also applies. So now I know something fun. A union B union C, the fraction of the whole surface area that's covered by any of these, is equal to the fraction covered by A plus the fraction covered by B plus the fraction covered by C minus the fraction covered by A and B minus the fraction covered by B and C, minus the fraction covered by C and A, running out of space, plus the fraction covered by all of them, B and C. There we go, just fit. Okay, so that's inclusion-exclusion principle. Let's start filling in some of these. Can anyone tell me any of these that you would like to fill in? Some of them are quite easy. Out of it.
So, like the first one, A union, B union, C, just like misses the background.
Ah, okay. So the A union, B union, C is the tricky one. It's not 1. A union, B union, C is not 1 because of this observation we made at the outset. There's this other copy in the back. There's a reason I wanted to say that, because the most common mistake is to say A union, B union, C, that's everything. Nope. It actually just misses the part in the back. Why? Because if you look at it, right, like if you go underneath the A part, you go under to here and you stop right before covering that back triangle. What about the B part, which is where you go over the pink thing? Go up and then back around and you stop right before entering that white triangle in the back, or the triangle in the back. The C, from here you go, wait, how do I do this? Anyway, from here you go up and over and then you stop right before that triangle. So actually the A union B union C, that one's interesting. That fraction, oops, I want to use this pen. That fraction is 1 minus x. Why did I call it x? Well, x is what I'm looking for. X is this fraction I'm curious about. Is that okay? Because of that, I'm going to label the last one as x. So I've labeled x is the intersection of all three, and 1 minus x is the union of them all. Can anyone give me more stuff? There are other things you can put in that are easy and actually really useful. Venkatesh.
So aren't the areas of just A, B, and C, it's just half of the
Perfect.
overall area?
Okay. And then now we get to the weird ones. What's the fraction of the area of A intersect B? I'm going to draw that. What is A intersect B? Let's just draw that over here. A intersect B, that corresponds to under the green and over the pink. Under the green, over the pink, it's like here. Oh, that's so horrible. Hopefully you understand what I tried to do here. I tried to highlight the part under. Ben, did you want to answer this one, or were you answering a different one?
Yeah, I was gonna answer the last one, but I guess for this one we could use like the work we did before. Like,
Yeah.
Maybe like something with the angle, so like the angle over, or 1/2 times the angle over 180.
Yes. So let me jump right to the angle over 360. Do you remember that? That's what we had before. Yeah, that's okay. This is the angle over 360, right? Look, the formula is coming together. I want to have a formula that involves the angles between these things, right? And it's appearing. There's one of the angles. I don't know which one this is. Maybe it's alpha. Hard to read because of that highlight there. Here's what I'm going to do. Ooh, erased too much. There's an alpha. That was an alpha I just drew there. So this thing is minus alpha over 360. You might see where this is going. Actually, each of those other things, what are they going to give us? Remember, the three angles are alpha, beta, and gamma. Christopher?
The others will just give you beta over 360 and gamma over 360.
Yes. So I'm not going to draw which one is alpha, beta, and gamma, but it's the whatever it is what it's supposed to be. Okay, so I need to solve for x. This suddenly looks doable. I have an equation I need to solve for x. So what do? I put all the x's on the same side. That's the right side. That's 2 x's are on the right side. I move everything else to the left side. So I have a minus alpha over 360 minus beta over 360 minus gamma over 360. That gives me an alpha plus beta plus gamma over 360. And what else? Somebody help me finish this. There's a gap here because there's something that needs to be stuffed in. What else? How do I close it? Okay, a whole bunch of people wrote minus a half because I had 1 on the left and 3 halves on the right. So, okay, minus a half. This is coming together. What happens if I do a common denominator? Alpha plus beta plus gamma minus 180 over 360 is equal to 2x. And that's exactly what you want, because then what's x? You just divide by 2, right? So I suddenly find out that the formula I wanted is there. X is equal to the sum of the angles alpha plus beta plus gamma minus 180 divided by 720. And that's the proof. So this basic combinatorial idea of inclusion-exclusion turns out to be extremely powerful. We can even use it to get into Carnegie Mellon University, and also to derive like this old formula, known for ages formula about the area of a spherical triangle. We didn't need any calculus. It's actually really interesting. So what we're going to do in the next few days of these lectures, we're going to talk about why inclusion-exclusion is true. We're going to talk about it with more sets. We're going to look at more applications and so on. But we're effectively now into a different part of the unit, which is all about inclusion-exclusion. Okay. See you guys next time.
Thank you. Thank you, bye.
I'll stop streaming the YouTube.